All right, what's up, guys? In this video, we're going to pick up some calculus here, and we're going to be doing some definite integration using Riemann sums. So we're given this integral here. It's a definite integral from 0 to 2, got 2x plus 1 dx, and they give us n is equal to 0.4. So we'll use the definition of the Riemann sum to evaluate this definite integral, and then at the end, I will show you how to evaluate it, basically evaluate the definite integral just in general, and our answers should match up. So let's just start out with the general definition for the Riemann sum as it pertains to definite integration. So if I have some integral from a to b of some function of x, or f of x, however you want to say it, remember that's just equal to the limit as n goes to infinity. And then we have our sum, I is equal to 1 to n. And it's going to be f of x sub I multiplied by delta x sub I. So let's clear up what a lot of this stuff means. So for the x sub I, remember x sub I, that's just a plus I times delta x. Similarly, delta x is just going to be b minus a all divided by n. Okay, so if you guys can see this, the lighting is a little bad. So I'm trying to adjust it here. Hopefully you guys can see it. Trying to adjust the lighting. I don't know if that makes it better. Okay, well, hopefully you can see it. All right, well, let's continue. So now that we have the definition here, we just need to go ahead and determine our A and determine our B. Let's determine what that is. Adjust this light. Hold on, guys. I want you guys to be able to see. All right, hopefully you can see. All right, so let's do that. So what is A? Sorry about the technical difficulties. I'm trying to adjust the lighting in the video because I want you guys to be able to see it. So what is A? Well, A is 0. Okay, and what would B be? Well, B would just end up being 2. Okay. So now all we really need to do is we need to go ahead and calculate delta x, and we need to get our x sub I and take it from there. So, all right, so we got delta x is going to be equal to b minus a all divided by n. So that means we have delta x is simply going to be equal to 2 minus 0 all divided by 0.4. And make sure you take your calculator. The answer to this is 5, I believe, but I will obviously check just to make sure. So it's basically going to be 2 divided by, yeah, it's 5. So you get 5. I'll put that right here. So this is what we get when we do delta x. We get 5. So x sub I in this case now is going to be equal to I times 2 over n. Okay. So we get 5i. All right. So now we've taken care of all the preliminary work. So now we have our definition, or we use the definition now in this case. So the limits, again, of integration are going to be from 0 to 2. That's where the A came from. That's where the B came from, just in case you might have got lost there. And then it was, or then the function is 2x plus 1 dx. And we're going to use the definition to evaluate it. So we got the limit as n goes to infinity. So you got I is equal to 1 to n, and let's start subbing this stuff in. So that's going to be 2 times 2i all over n plus 1 multiplied by 2 over n. Okay, let's continue to simplify. You want to try to simplify this down as much as possible before you try taking the limit. I tell people all the time, don't try to take the limit too early. If you try to take the limit too early, it's just going to be messy. So try to clean the stuff up first before you try taking the limit, which we would have to do, which essentially we would have to do anyway. Okay, so again, it's going to be I is equal to 1 to n. And notice how I'm going through all the steps. I'm not leaving basically anything out. So we got 4i all divided by n. Again, all I'm doing is the simplification. This would be plus 1 multiplied by 2 over n. So hopefully you're with me on where I'm at. And you want to make sure that you're writing this limit stuff down every single time. So, because if you're not writing it down, some professors will take points off because, you know, you're not continuing to write it. Because basically, if you don't write the limit notation, you're basically saying that you're done taking the limit. And some professors are really, really big on that. And which I understand. But just be aware of that. That's all I'm saying. So it's going to be I is equal to 1. And then it's all going to be to n. And we're just going to continue to simplify it. So it's going to be 8i this time all over n squared plus 2 over n. Okay. Now, what I'm going to do is I'm going to pull out, so we got the limit as n goes to infinity. I'm going to pull out an 8 over n squared. So then we'll have from I is equal to 1 to n, and then we'll just have I plus 2 over n. And then we'll keep our 1 on the outside here. All right. So let's keep going with it. And all of the simplification is going to, where do I want to put this? I'll put it right here. And all of the simplification that we're doing is actually going to make the limit easier to take. All right, let's pick up where we left off. Now, how do we deal with what we had? So, get my sheet, sorry. Okay, so remember, we had the limit. I'll just put it right there. So remember, we had the limit as n goes to infinity. And remember what we had. We had 8 over n squared. I is equal to 1 to n. And I just pulled it out, and you'll see the purpose of pulling that out in just a moment. But since I had to go to another sheet, I'm going to just go ahead and write it down. That way you don't have to try to guess as to what we had on another sheet. So now how do we deal with this? Well, we can use the following formula for this. All right, so the formula we're going to use here. So if I have sum from k is equal to 1, basically to n, for 1 over n. Oh, excuse me. That means that k is going to be equal to 1 over n multiplied by n plus 1. That's the formula that we're going to use for this. And we basically just have to substitute the information in. So that means that we get 8n squared times 1/2 n plus 1. As you can see here, the n's will cancel out. So now, in this case, if we simplify, we'll just get 4 n plus 1 all over n. Okay. And now we put our information in there. So now we got the limit as n goes to infinity in this case. And we'll have 8n squared times 1/2 n times n plus 1 plus 2 over n multiplied by n. And notice how I'm meticulously going through all the steps, not leaving anything out. So this becomes the limit as n goes to infinity, and we clean it up. So I'm going to clean this up. I'm going to write this as 4 times n plus 1 all divided by n. And then this will basically just be plus 2 because the n's over here will cancel out. And that's where it's at. If you want to, you don't have to, but if you want to, you can even factor out a 4 if you want. You don't have to. If you want to, you certainly can. And if you factored 1 out, well, you'd have 4, and then you'd have 1 plus 1 over n plus 2. Now, why would that be? Why would it matter if you factor that out? Well, maybe if you're familiar with how to take the limit for something like 1 plus 1 over n, that might be a lot better than maybe 4 or 4 times n plus 1 all over n. Maybe it might be a little easier for you to identify how to take the limit at infinity for that. So that's another way to do it, just in case, the other part looks confusing. So now we take the limit, and let's split it up here. So now we got the limit as n goes to infinity. And again, I just took the 4 out, so it's going to be 1 plus 1 over n. Now remember, we're adding plus 2. So if we want to use the limit properties, as it pertains to, our limits, we can break it up a little bit and do it this way. And now we take the limit and we see what we get. So what do we get here? Well, we'll clearly get 4 here. And the limit as n goes to infinity for some constant, it's just that constant. So in this case, the limit as n goes to infinity for 2 is just 2. So this becomes 4 plus 2, which we know is simply 6. And so the answer to this problem is simply 6. So that's going to be our final answer when we actually use Riemann sums to do it. So Riemann sums. Now what I'm going to do to show you that the answers match up, the final answer is 6, but just to show you the answers match up, I'm going to go back and I'm going to evaluate the integral just in general, just to kind of show you that our solutions should match up. If they don't match up, you did something wrong, because they should match up. So in our case, again, when we used, what was the integral? It was from 0 to 2. When we used the Riemann sums plus 1 dx, and they gave us that n was equal to 0.4, we ended up getting 6 when we evaluate the limit. Or excuse me, when we evaluate the definite integral. Okay, now let's prove that 6 is the answer by just evaluating the integral in general. So from 0 to 2, we had 2x plus 1 with respect to x. Okay. So this is just the integral from 0 to 2, 2x dx, plus the integral from 0 to 2 of 1 dx. Okay. And so clearly, this would be 2 times x squared over 2 evaluated from 0 to 2. That'll simply just give us a 4. If we integrate 1 dx from 0 to 2, okay, we're integrating with respect to x. We just have a constant there, so that's just going to be x, basically from 0 to 2. And in this case, we would also get 2 when we actually, applied the fundamental theorem of calculus and subbed in the upper and lower limits and, basically subtracted them away. So we would essentially just end up getting plus 2, which we know is, in fact, 6. So that would actually be the answer if we actually just evaluated it in general. So you just have to make sure that the answers match up. So they matched up when we used the definition of the Riemann sum. It matched up over here, and it matched up over here when we actually did it by hand. And that's pretty much how you do it. So a bit of a lengthy example, maybe a little bit too much, but again, that's basically how you evaluate it. So let me know if you got any questions about it. I'll try to address it. So I'll see y'all next time.